Okay, we're starting. We're going to continue with our trig review and then move on to talk about inverse trig functions. So we'll need this trig review to a little bit to do with inverse functions, but it will actually be important in the future when we're covering a new topic called polar coordinates, which is a very important topic to cover, especially for multivariable. So really being up on our trig is going to be very important coming up. So I thought we'd kind of go through a nice review. Again, kind of rushing through it, but I figured that most of you guys know most of this already, and if not, I show you guys some tricks that I think are quicker than a lot of students learn to do things. So, if you're one of those people where you learned all the trig values, or your professor gave you that huge circle, and you had to remember like 24 values on that circle. Very inefficient, I believe. I think you do that table and you learn all students take calculus, you know everything in that table already. And so things like that I think are going to be important, because later on you will be expected to know your trig well enough to know all that stuff pretty quickly. It shouldn't be the main thing when you're doing trig in this class. Okay, so one thing I believe I did not do is the graph of tangent, so let's quickly just do that. Knowing some of the trig graphs are important. Sine, cosine, and tangent you should know. The other ones you can kind of figure out, but I probably wouldn't expect you to know them by heart. But the graph of tangent you should kind of know by heart. I'll just give you what that graph is. Remembering that the graph of tangent is actually sine of x over cosine of x, that's how you get tangent of x. That's clearly undefined every time the sine is 0. And we know that sine, every time the cosine is 0. And we know that the cosine is 0 at every odd multiple of pi over 2. So the first one is going to be at pi over 2. Then it will happen at 3 pi over 2, 5 pi over 2, etc. And 5 pi over 2, and that's so I'll just draw a few guys here. It also happened at minus pi over 2, minus 3 pi over 2, and going back. But the main period is the guy in the middle right here, and the function looks like that. Right? And again, it's because of all students taking calculus why it's positive in the first quadrant, but it will be negative here, because this would correspond to the fourth quadrant. And so this pattern actually repeats. Right? And it's obviously 0 every time the sine is 0. So it'll hit 0, of course, at 0. It'll also hit 0 when you hit zero everywhere sine is 0. The one that you really need to remember is this middle one. And when we're talking about the inverse trig functions, that's the one that's going to take care of it, that we're going to need to know. So we spoke about sine and cosine being the principal period is going to be where you're between 0 and 2 pi. For tangent, the principal period is between minus pi over 2 and pi over 2. That's the piece of the graph that you're expected to remember, and you realize that that pattern actually repeats. Okay, so besides that, what else do we have to do? Yes, I spoke about that. Just leave the graph of tangent. So we did talk about the addition, double angle, and half angle formulas. Okay, those will come in useful for integrals. And so now it's graphing transformations of these functions. We're going to focus on sine and cosine. But in general, you could actually apply this logic to other things. So And we're just really applying our transformation rules, but again, it's something that you could slowly kind of work your way through this, but it's nice to just be able to do something quickly, especially if we get to polar coordinates. We're going to need to know how to graph these things relatively quickly. So we can be given two different functions, a sine k of x minus b plus c, or a cosine of k of x minus b plus c. The following hold. And this is just really applying the laws of transformations on these trig functions. And I'm kind of going to illustrate over here. I'll give you the rules first and then I'll illustrate over here what I mean. Okay, so given this, right, and your A, your K, your B, and your C will be numbers, okay, constants, okay, but from that, if you're given a graph in that form, realize that if you take the absolute value of A, this is the amplitude of this function, right? It's how far you rise and lower from the base of the graph, and I'll talk about a little bit more about that. If you take the B, this is called, the technical term is called the phase shift, but you really can think of it as just the horizontal shift. If you look at C, this is the vertical shift. C basically identifies your new baseline. Normally if C is not here, the baseline is 0, but you can shift that up or down. Another thing that's important to know here is that if you take 2 pi divided by the absolute value of k, this will give you the period of the function. Right? So that's the interval that gives you that pattern that's repeated forever. Okay, that's how long the interval will be the period. There's something, I don't know what the technical term for this, but I'll refer to it as the subinterval. And this is really just something to facilitate you graphing something really quickly. This is the period over 4. We'll talk about why the period divided by 4 specifically is important for these functions. The appropriate graphing interval, unless otherwise stated, so in general, you'd want to start at B and then go for 1 period. B plus 2 pi over absolute value of k. In the future, we'll actually always want to figure out what it's doing between 0 and 2 pi. In the future, usually we care about what is going on between 0 and 2 pi, regardless of the period of the function or what it's doing otherwise. Right? And you'll see why that's important later on. But for now, if you're just given this and you're back in pre-calculus class, they'll expect you to draw the graph between here. So let me illustrate on the graphs how these numbers will actually play out. Okay, so here you have first of all, I'll draw it over there. But let me kind of explain where this is coming from a little bit. So why the period over 4 is important is because sine and cosine comes in 4 sections essentially. Right, so if you look at the graph of sine, for example, right, you can actually sort of create a grid that has 4 sections in it. And these are 4 sections where something important will happen. It will either hit a maximum or a minimum, or it will hit 0. So if you're looking at this whole length here is called the period, but each of these sublengths here is the period over 4. Right? And you can know how a sine graph is going to behave based on the fact that it is a sine, it will behave in a peculiar way in each of these 4 sections. So the original graph of sine, it starts at the baseline, then it hits a maximum, then it hits the baseline, then it hits a minimum, then it hits the baseline again. That's what makes something a sine graph as opposed to a cosine graph. How you start the graph off. A sine will always start at the baseline. It will always start in the middle, right? Whereas the cosine has a different kind of behavior. Again, you could draw this grid. You'll split it up into 4 equal sections. And so the cosine has a different behavior. It actually starts at the top of the grid. Then it'll hit 0, then it hits a minimum, then it hits the middle, then it hits the top. So the cosine graph will look like that. Of course, if you take the negative of the sine, this all flips upside down, but the sine will always start at the baseline, at the middle, and then either go up or down depending on the sign of the coefficient. The cosine will actually always start at the top or the bottom. Okay? And that's kind of why knowing the period over 4 is important. You can actually know the behavior in each interval, and that will actually help you out in sketching something really quickly. Okay? But at the end of the day, this kind of summarizes what a picture of a typical sine or cosine graph would look like in terms of what you put in first or second or third or fourth. So the first thing you're kind of going to want to know is the baseline, okay? And that's actually going to be given to you by the C. So let's say C is some positive number. So my C comes here. That's your new center line for the graph, okay? And so C is kind of the first thing you put in. So one, you first figure out where C is. The second thing you're going to want to figure out is the amplitude, which you can take by taking the absolute value of the guy in front. And what the amplitude is how far you move up and down from this baseline. So you'll move up by A units, and you'll move down by A units. And so that will form the top, and that will form the bottom. So that's kind of what you'd think of doing second. What you'd think of doing third is figuring out the B, the phase shift, the horizontal shift. Let's assume this B is a positive number, so I have x minus something. So let's say the B comes here, that's your B. The fourth thing you're going to want to do right away is sketch that grid. Now this is a sketch. It doesn't actually matter what scale you use. It's a sketch. So you just randomly draw in lines. You're going to draw in 4 lines. Right? And you literally put the numbers afterwards. Right? So you're going to here, you're going to start, this is B. This would of course be B plus the period over 4. This will be B plus 2 times the period over 4. This will be B plus 3 times the period over 4. And this will be B plus the period. Right? And those numbers you can literally compute very quickly and just write them in after the fact. You draw the grid first. Write in the numbers for subintervals. Right? And the numbers will always have this form. You start at a certain point, which is going to be given to you by this number here. And you can always, the entire thing here is the period, which it should have length. The length of this interval is going to be 2 pi divided by the absolute value of k, which is going to be the number that's in the coefficient of the x. And so at the end of the day, this end point should be b plus 2 pi over k. Right? That should be what the value is. So the interval will start at b, it will end at b plus 2 pi over the absolute value of k. So at the end of the day, when you're adding these numbers together, you need to make sure that the last number you get actually corresponds to this number to make sure you're not making a mistake. It's a nice little double check you can do in the middle of your graph. So once you actually have this grid down, then you basically sketch based on the grid pattern. By grid pattern, I mean knowing whether or not you have a sine or cosine, you'll sketch basically this way. So let's say, for example, I knew this was y equals a sine ax minus b plus c, and where my a is positive. I know after I construct this grid, I'm going to start here, go up, go to the middle, go down, go to the middle, and my graph would end up looking like this. Okay. So it's going to be like a sine graph, but it's shifted or stretched or squeezed in some way. And the quickest way to get to know how it's going to be shifted or stretched or squeezed is to go through this checklist here. Kind of want to do it in this order here to make sure everything falls in line, because I kind of, that's how you would sketch it basically. So now it will take some practice, but you can just practice sketching a bunch of these and you will actually get relatively good relatively quickly. So maybe we can do a couple of quick examples. Let's say I have y is equal to minus 2 sine x minus r over 4. Let's not go to that. Plus 1. Let's do that. So you're faced with a graph like that, you want to draw it. So here we're going to go through, we're going to figure out all these numbers. That's the first thing. So here my absolute value of A is 2. My B is pi over 4. My C is 1. What's my K? 1. It's also 1. That means that my period is going to be 2 pi. Well, 2 pi over 1, which is 2 pi, which means my period over 4 is going to be 2 pi over 4, so it's pi over 2. Right, so I know that. Okay, now let's put this all together, essentially. So once you figure those numbers out, you come here down to the graph. First thing you do, put in our baseline. So that's at 1. That's the baseline. My amplitude is 2, so I'm going to go up by 2, that hit 3, down by 2, that'll be minus 1. These are drawn as broken lines or very faintly because they're not actually a part of the graph, they're just helping you to draw the graph. Our B is pi over 4, so I'm going to just call somebody here pi over 4 and start cutting there. I will then immediately proceed to draw 4 sections of this grid. Right? So this I know is pi over 4. This guy is going to be pi over 4 plus pi over 2, right? Because that's my period over 4. Okay. So I start here and I add that guy 4 times in order to get everyone. Right? So pi over 2 I can think of as 2 pi over 4. So I know that this guy is going to be 3 pi over 4 plus 2 pi over 4. This guy will be 5 pi over 4 plus 2 pi over 4. This guy will be 7 pi over 4 plus 2 pi over 4. This guy will be 9 pi over 4. Right? I just keep adding plus pi over 2. Plus pi over 2, plus pi over 2. So now I have my grid and I have all the important points of that grid. And now what I do is I realize that this is actually a sine graph. It's negative, so I'm going to take the sine pattern and I'm going to flip it upside down. But I do know the sine pattern starts in the middle. So this graph is going to start here. Then instead of going up because it's negative, it's going to go down. Then it's going to hit the middle. Then it's going to hit the top. Then it's going to hit the middle. And so at the end of the day, this is my graph. And so now I have the graph. I also have a lot of important information. So for example, if someone were to ask me, what is the maximum of this function? It's 3, right? When does it hit the maximum in the principal period? It's at the point 7 pi over 4, comma 3, right? I can tell a lot of information about this graph right away. I can also sketch it right away. Let's do something that's going to be directly a little more relevant later on. So let's say something like y equals 2 cosine 2x plus 1. So the idea is we will actually be sketching things like this in a completely different coordinate system other than the xy plane. But knowing how to sketch it in the xy plane and then transferring it back is going to be very convenient. Okay, well, let's look at something like that. And here, I will actually give you a specific requirement. Sketch on 0 to 2 pi. So whatever this interval happens to be, keep extending it until you fill up the 0 to 2 pi level. So being able to do something like this is going to be very nice when we're sketching things called polar curves, which will happen in the last quarter of the semester, probably towards the last quarter. So you see something like that, you're first going to just get to the numbers again. So our A here is 2, the B here is 0, the C is 1, the K is 2, right? Because you can factor, you can write this as 2 times x minus 0 plus 1. The cosine of that. Which means here the period is going to be 2 pi divided by, absolute value of 2, that's actually just pi. Right? So the entire graph happens in a span of pi. But of course, I want you to sketch it on 2 pi, so you're actually going to have 2 periods of this graph being sketched. You can look at the period over 4. Well, that's literally going to just be pi over 4. So each quarter of one period is going to be in the pi over 4 section. Now let's actually do this. So now we can sketch this graph here. The baseline is 1 again, so I'm going to go here 1. The amplitude is 2, so I'm going to go up by 2, down by 2. Up by 2 gives me 3. 1 plus 2 is 3, even in Calc 2. And this will be minus 1. Our B starts right here at the 0 mark. So that's nice. But I'm still going to split up my grid. However, I know here that the period is pi. So when I set up this grid of 4 things, this actually only takes me up to pi. Right, so I'm going to extend it even further. So here I'm going to have 2 of these grids. Going all the way up to 2 pi. I know that my period over 4 is pi over 4, so I start at 0, add pi over 4. Add pi over 4, this gives me 2 pi over 4. 3 pi over 4. 4 pi over 4. 5 pi over 4. 6 pi over 4. 7 pi over 4, 8 pi over 4 hits the 2 pi mark. And so now, I'm just going to graph the pattern for a positive cosine. Cosine I know starts at the top. So this is going to be the first point in the cosine graph, then it's going to hit the middle, then it's going to hit the bottom, then it's going to hit the middle, then it's going to hit the top, and it's going to repeat that pattern. And so that's going to be the graph of my cosine. And that is the required sketch. Now at first, later on when we're doing these polar sketches, your book kind of suggests, just like when you're learning to graph way back in algebra, they suggest, oh, just write out a table of values, plug in a bunch of points and blah, blah, blah. Usually that takes forever, and usually with something sufficiently complicated, you're not sure if you're plugging in enough points to get a clear picture. But doing something like this, you'll always know what that picture should look like. Often, by the way, pretty much always, especially in the future, often we'd also like to know, would also need to know, and it's actually going to be very important to know, when the graph hits 0, right? As in, what are the x-intercepts of this graph? So that would be like points like here. These will be points of interest. So how do we do that? You set it equal to 0, of course. All right, so you have 2 cosine 2x plus 1 equals 0. How do you solve that? What are your x values? It's your turn. Yeah?
Subtract 1 on both sides.
Subtract 1. And divide by 2, so you get minus a half. How do you solve that? Sure, but we don't really know the inverse yet. And by the way, the inverse technically is going to miss some of the answers. So we want to think more generally now. You kind of want to think in the affirmative rather than the reverse. So when you see something like that, what you really look at is you kind of ignore the signs for a second, but you kind of look at that. And then you're going to look at the table that I gave you guys earlier. So at this point, this table is going to be burned in your brains. And so this you'll be able to do. This is pi over 6, this is pi over 4, this is pi over 3. Can you guys remind me how to fill out this table? Somebody?
1, 2, 3.
On the top, 1, 2, 3.
3, 2, 1.
3, 2, 1.
Square root.
Square root everybody. Divide everyone by 2. So the point of interest for you is where the cosine hits a half. You realize that that hits a half here in the pi over 3. However, then you consider the negative sign. That's going to tell you what quadrants you need to be in, right? So that means if you're doing a circle here, here where the pi over 3 is where the cosine is going to hit positive a half. But because we know about all students take calculus, right? Where's the cosine negative?
Quadrants.
It's in quadrants here and here. So I know the answers I care about are going to be the reference angles for here and here, right? But this just comes down to us slicing up that pizza in the same way we did before. From 0 to pi, we slice it into 3 pieces. So it's the first slice, the second slice, the third slice, the fourth slice, the fifth slice, the sixth slice. So this guy is you take 2 slices to get to here, that's your 2 pi over 3. And you take another slice to get over here, that is going to be 1 slice, 2 slice, 3 slice, 4 slice, that's your 4 pi over 3. Now that will give you the first 2 answers, so you still want to keep going around the circle to get the other ones, right? So this is going to be equivalent to, so it's 1, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3 will be the next one. 9 pi over 3, 10 pi over 3 will be the next one. Okay, so we have the first 4 answers. And by the way, if you just use cosine inverse, it would miss these answers. The cosine inverse doesn't extend that far. So it's just a matter of you slicing up the circle and counting off the number of slices you need to get to a certain point. And you know the points you need to get to are the guys that are in the second and third quadrant because the cosine is negative there. Yeah.
How'd you get 10 pi over 3?
Because if you have the circle, here's where angle 0, you were absent for this. This is, of course, where angle pi is. So when you see pi over 3, it means you take pi and you divide it into 3 equal sections. You can do that for the top and the bottom. And you can determine which sections you care about. So in this case, we care about those 2 lines. And you're literally counting off the number of sections you need. So in the first case, we have 1, 2 sections to get to here. Then I need to go to 1, 2, 3, 4 sections to get to here. That's the first 2. Then I need to go all the way around. So this goes 1, 2, 3, 4, 5, 6, 7, 8 sections to get to here again. That's your 8. And then I'm going to do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections to get to here again. Yeah.
Wouldn't we have to divide by 2 after we have the pi over 3 to account for the 2x?
Yes, we're looking at the angle here. This is our theta. Right?
Oh, okay.
So in this case, I'm thinking of this guy as theta.
Okay.
Yes, we're going to divide by 2 eventually. But you need to know what to divide by 2. This is how you get those numbers that you want to divide by 2 in the first place. Yeah.
So if we have pi over 3, are we dividing the circle into 3 parts or 6 parts?
3 parts. Well, the full circle into 6.
Oh,
But you divide pi into 3. Pi is only half a circle.
Okay, so.
The full circle is 2 pi. So technically you'll divide the entire circle into 6.
Okay.
But you think of it as dividing half of it into the number and then you just copy it down.
Okay.
Okay. So essentially what this means is from this graph you realize that you want the first 4 answers. So I only do this as far as the first 4 answers go. And so what this would mean is that my 2x, the angle, is going to be equal to either 2 pi over 3 or 4 pi over 3 or 8 pi over 3 or 10 pi over 3. There are many more answers, but I do not care about those answers. And therefore, my x would be, I would divide each of these answers by 2. So it would happen at pi over 3, it will also happen at 2 pi over 3, it will also happen at 4 pi over 3, it will also happen at 5 pi over 3. And that's actually the numbers that you'll hit the axis here. So this one here is actually at pi over 3. This one here is at 2 pi over 3. This one here would be your 4 pi over 3. This one here would be your 5 pi over 3. By the way, I'd like to mention here, in the context where we actually need to do something like this, at this point, we would make it through maybe a third of the problem. So it's actually important that you're able to do this part very quickly. And that's kind of why I'm taking the time to go over a trig review, because I really need you guys to get back on this. It's probably a long time since you really focused on trig a lot, but we are going to need to have super focus on trig for the future, because all this stuff should really be happening in the background. The thing we're going to be using this for hasn't started yet. I haven't actually broken out of pre-calc at this point. This is technically something you should know since pre-calc, but it is something that you're going to have to know, because we're going to do all of this, and then we're going to have to transform this to an entirely different coordinate system and do things in that coordinate system, which is called the polar coordinate system. Right? It locates points different from the xy plane, how the xy plane gets it. Okay? So there are some times when I might say, graph the polar curve, blah. You'd have to do all of this, and then you can graph the curve. And then I might ask you to talk about, oh, find the area inside this part, or find the area inside the small loop, find the area inside the big loop, find this, find that. And it's all going to be dependent on this. And there are times when just drawing this graph can help you answer those, because it turns out one of the reasons why hitting a 0 is important is they define the endpoints of a loop. which is going to be important to us. So you can realize that the area described by this guy is the area of a small loop, while the area described by this guy is the area of a big loop. And so you can, there's a lot of intuitive benefits from being able to do this very quickly. But technically, at this point, this is review, that's what you should use. And I believe that's everything I think we need to know for now. Well, we are going to start with the inverse trigs from the basic principles as well. So I guess that's the first part of the next section is also a lot of review. But we're going to want to get to the calculus of the matters pretty quickly. So now we are officially in 6.6. We're going to talk about inverse trig functions. And their calculus. Mostly we're going to talk about derivatives of the inverse trig functions at this point, but the integrals will be in the next chapter. In chapter 7 we'll cover the integrals using trig functions. So it turns out that there are many sufficiently complicated cases that we need an entire section of a chapter to do with them separately. One thing I want you to note is that none of the trig functions are actually one-to-one. So to find their inverse, because I don't remember if I mentioned this, but you can only find the inverse of a function if it's one-to-one, and the codomain is equal to the ring. Okay. So to find their inverse, we must restrict the domain. For instance, I'm going to restrict the domain for y equals sine, y equals cosine, and y equals tangent. So we decided to restrict the domain in special ways here. So our sine graph looks like this. And obviously it continues backwards. So how we decide to restrict the domain for sine, we decide to cut this off at pi over 2 and minus pi over 2. So the only part of this graph that we're going to be flipping is this part of the graph. Right? And for the purposes of coming up with inverse functions, we ignore literally everything else. And we only care about, when we're talking about inverses and we want to figure out graphs of inverse and properties of inverse, it will only work in this window. And so that's why it will miss some of the numbers. An inverse function will only give you the 2 answers, but to get more, you kind of have to keep traveling around the circle. For cosine, we restrict things a little differently. This one starts at the top and then goes here and then goes here. And we actually cut it off here, between 0 and pi. So this part of the graph is what's important to us when developing the inverse function. And we ignore everything else. Tangent, we also know that graph. This is at pi over 2. This will be at minus pi over 2. And we restrict the inverse. We restrict the graph for the inverse here. So we kind of ignore all the other sections except that section that's right in the middle. Okay? So by doing that, now these pieces of the graphs that are left over, they pass the horizontal line test, they are one-to-one, and we can actually do an inverse property. So now this means start by finding the graphs of the inverse functions. Remember, the rule for this is to flip or reflect. Flip is the right word. Reflect in the line y equals x. This means you get the following. The graph of y equals sine inverse of x. Okay. I also want to point out that that inverse is a notational thing. It is not the same as saying 1 over sine of x. This guy is actually equal to cosecant of x, which is, they're very, very different functions. So for the sine inverse, you're pretty much going to think of the line y equals x, and you're going to flip this guy in that. Okay? So what do you think we're going to look like? It's going to start here. And look like that. You can also, so this is just a graph that has this part. It does not extend further. But based on what we know about inverse functions and the original graphs, we can actually come up with some limits for this guy. What are the limits here? What were your limits here? What was this limit? 1. And this? -1. Remember, for inverse functions, your x and y values switch roles. So which means your x values here are the y values from there. So this would be at -1, this would be 1. Similarly, this will go to a maximum of pi over 2, that will go to a minimum of minus pi over 2. So everything switch, your x and y switch places, the graph flips over the line y equals x. So you pretty much take this graph, draw this line here, and then you kind of take the mirror image of this guy. Would that? Is that what that looked like? Did I draw cosine inverse? I think that's. Let's do cosine.
You just have a mapped.
Huh?
You have
I think.
-1 mapped to positive pi over 2, and
Yeah.
1 mapped to
I think it's actually flipped
You
the
just need
other
to
way.
reflect over the y-axis.
I think I flipped in the y-axis, not the line y equals x.
Yeah.
Because this it should map this way. Sorry about that. Right, -1 should go to negative because of how the sign works in the first octant, but it looks this way. Because the old function, the old sign was this way, right? And so this is the line we flip it. That makes sense. So this was the old graph. I reflect in this line, so it just falls right over there. Yeah, okay, so that makes sense. See if you guys are paying attention. You do the same idea with the cosine, let's actually be careful this time. Y equals cosine inverse of x. So you're going to basically draw the line y equals x. I wrote in the numbers. Okay. So what is that guy going to look like? Let's look at the limits on the grid. Like, what are my limits here? This is a 1. This is a -1. This is at pi, right? 0 to pi. Which means that this graph is going to flip from, on the y-axis, we're going to be from 0 to pi. And then on the x-axis, we are going to go from okay. And what are the guys that are mapped to different people? The 1 is connected to everything's going to happen to this guy. So here we have when x is 0, our y is, so this is x comma 1, our y is 1. Right? So in this graph, the opposite should be true, right? So we should have 1 comma 0 on our graph. And so that would give us this point. What about this point here? This would be the point where our x is pi and our y is minus 1. So over here, we should have minus 1 comma pi on our graph. So we should know like here, and this guy is, draw this guy like that. Yes. When we look at y equals tan inverse, oh, we're almost out of time. This is pi over 2. This entire thing flips the other way, minus pi over 2. This graph looks like that. It's also no coincidence that I can draw this graph very quickly while these guys have to remind myself how to figure them out. Because in practice, knowing these graphs aren't actually that useful, but knowing this graph is super useful. We use the graph of tangent inverse all the time. Like usually in any context where I'm thinking about this inverse sine or cosine, I'm not going to be using the graphs. We'll see when we use those as well. But we'll stop there. We'll do the calculus of them on Tuesday. So we're not finished with that. We'll finish, yeah.
When can we expect the midterm? Or like the first test?
Maybe 2 to 2.5 weeks-ish for the first test.
No homework for.
No homework for this section. We didn't finish it.